Today we have LPC, linear predictive coding. So, what it does, instead of transmitting the whole signal, LPC creates a model that can be used to predict the signal. Imagine a sender and a receiver. The sender calculates prediction coefficients using first n, in our case 10, for example, samples of the signal. Sender tests his prediction model to predict the whole sample based on his prediction. Sender calculates the errors between the signal and his own prediction. Thus he calculates the difference and stores it. Transmitting the signal as a whole is not needed. Therefore, the sender sends first n, in our case 10, samples and the prediction coefficients. Also he sends the errors. There's as big number of errors as discrete points of the signal. However, errors are smaller and require less bandwidth to be transmitted. The receiver can now try to recreate, to predict the original signal using prediction coefficients. Prediction will not be perfect, but nevertheless errors are known. Receiver will simply subtract or add the errors and the exact signal will be eventually produced. If we transmit 10 samples, the 11th can be approximated as a linear combination of past samples. For example, 10. And here there is a formula. This is for the prediction part, this is for the error part. It's a linear combination. It's a multiplication of prediction coefficient by some values plus error. Now we can reproduce real value. In order to determine the coefficients, aka prediction coefficients, we need to minimize the error, because the smaller error means that less we transmit. Here's the signal value at some point, here's the linear combination, and here this is the sum of square errors. In order to obtain actually the prediction coefficients, we will use Yule-Walker equation. The matrix F can be obtained by the input signal, and then we can solve the equation using 3 different methods which have different complexity. I'll show them later. Yes, and from here each row is a linear equation and can be solved for AK. So we get matrices F by this formula, and we have to keep in mind that E squared is minimized also by the formula below. And 3 methods with different complexity. So first of all is Gaussian elimination. It's O n cubed. Cholesky decomposition takes some special properties of the matrix into account. It's only for symmetric matrix. And Levinson-Durbin autocorrelation method. It requires Toeplitz matrix and symmetric matrix. It takes symmetry and Toeplitz of F into account. It's the formula here for the Levinson-Durbin. LPC is used in GSM, and actually it can be used in any system where you really care about how much will your signal weight, how much bandwidth will it take.